The broadcast is now starting. All attendees are in listen-only mode.
With ABB's wind power team. I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question, please use the question box on the GoToWebinar panel. We will answer as many questions as possible at the end of the event. Please ask your question during the presentation so it will be available by the end. Today's webinar is being recorded. A link to the recording will be emailed to you following the event. Feel free to forward the link to people you know could benefit from the presentation. Today's speakers are Dennis McKinley, Mietek Glinkowski, and Joe Fox. Dennis McKinley is the director of ABB's wind power business in North America. Dennis would like to open today's webinar with a few words about how ABB views the wind power value chain.
Thanks, Sarah. After working in the wind industry for a few years, we came up with the wind farm value chain and decided to host a 4-part webinar series on it. We've already done planning and consulting previously. Today we'll be doing connecting, and our last one will be on operating and maintaining a wind farm. I hope you get a lot out of these webinars. We're looking for feedback from you on future webinars that you'd like to hear about as well. Next. So ABB has been in the wind industry for some 30 years. This landscape drawing tries to highlight some of the areas that ABB provides products and services today. Everything from planning for the farms on the front end of farms to the electrical equipment that resides up inside the turbines, things like generators, converters, transformers, low voltage products, and also the electrical balance of plant down on the ground or in the water. So you can see we've got a pretty comprehensive offering for the industry. And again, today we're going to be talking specifically about connecting the wind farms into the grid. Next. So today's webinar, our goals are highlight to you folks a little bit about some of the challenges that we've seen or encountered when connecting power to the grid, some of the different solutions that are available out there that can overcome these challenges, and we'll also be discussing some real-life examples from some of our subject matter experts on the phone. With that, I'd like to turn it over to Mietek Glinkowski.
Thank you, Dennis. I would like to talk to you about some of the engineering challenges that are related to wind energy. And again, just for clarification, we'll not talk about challenges as environmental impact and other effects. So we're trying to focus on the technology specifically. And also, as Dennis mentioned before, will be particularly related to connectivity issues. So assume that we have a wind farm or have a plan for it, and assume that that we want to connect to the grid. There are a number of challenges that industry faces, and what I'm listing here on that slide is just 4 bullets showing some of them. Clearly, probably on top of the list is variability of the resource. We know wind doesn't blow all the time, and as other renewable energy, particularly solar, there is a cycle associated with the resource availability. So it is a main challenge, how to provide electricity when it's needed, not necessarily when it's available. So we'll talk a little bit about that. And the second one is a difficulty of tying renewables to the grid. And that particular bullet refers to reserves, or spinning reserves. Again, if you just think of the variability of the wind, if I have a certain megawatt installed in the wind energy, and if the wind is not blowing at all, then obviously these megawatts have to be replaced by some reserves that will pick up the load when the load is present. So there is a balance of how much of this reserve is really needed, and we'll talk a little bit about that. There's also the other grid requirements, and I think one of the important ones is reactive power compensation. Again, That has to do with normal operation of the grid, as well as situations like short-circuit currents or faults in power systems in general, and we'll talk a little bit about that particular one. And we'll try to touch also a little bit on the power quality part of it. I can go to the next slide, which is slide number 9. It shows a little bit of that connectivity challenge from the point of view. And the variability has two aspects of this. We all know it's a function of where we are, where the wind farm is, so geography is important, as well as a time variability. And just those two slides show, first on the left-hand side is a map of the U.S. With color scheme showing different classes of wind resource. On the right-hand side, just for a reference or comparison, we'll show sort of a expanded map of the planet from the solar point of view. And again, both of these resources from this point of view are similar in terms of the variability. And one could ask a question and say, well, I mean, we don't really have the wind as a resource we can count on. It's not really something we can dispatch, because we don't have basically control over the environment. Why we bother with this? And well, and the environmental reasons and all the global warming and renewables important of this is one of them. But the other one that people often don't realize is that there is so much of that resource available, and what we have right now in the United States available as wind energy, I think the last count that I made was about 60 gigawatts of energy that we have installed in 2013. It's about, I think, maybe 6% of the total energy, electricity energy in this country. But if you look at the theoretically available wind resource, and you take only certain states, especially in the middle of the country where you see most of the colors are, then the availability is orders of magnitudes much higher than what we actually harvesting. So that is, again, potential that is untapped. And I think this is why, with all the challenges in there, we really are trying to utilize this resource even to a greater scale. So it is an untapped resource. If we can move to the next slide, please. Let's talk a little bit about the requirements for the reserves. So again, theoretically, if you assume if there is a wind or there's no wind, then I either have this power available at the maximum rating, or I don't. So what do I do? I mean, theoretically, you would think that I need the same amount of energy is spinning reserves to account for the missing wind. So if I don't have the wind, I have to have a spinning reserve of X megawatts. If I do have the wind, obviously the spinning reserve is not needed, and obviously wind is providing that energy. So you'd think it's a 1-to-1 ratio in terms of how much reserve I needed. Well, it's not actually the case, and this is a graph showing several different studies and different experiences from various countries, not just in the U.S., in terms of what these reserves really should be, depending on the percent of wind penetration. So clearly it's not 1-to-1, and you look at the on a scale on the y-axis, the increase as a percentage of wind capacity at the maximum is about 18% or so. And even that study, which is actually a study coming from the UK and several years ago, I think it was a little bit on a conservative side. So if you look at the bulk of the estimates in the industry, you probably find these spinning reserves of the order of 10% or less. That means that for every 100 megawatts of energy that we produce with wind turbines, we need about 10 megawatts or less on average in terms of spinning reserves. So it is not 1-to-1, and it's not zero, of course, but on the average is about 10% or less. The other thing that I really want to mention, and it's an important, I think, message that hopefully you get out of this presentation, is that the the reserves are really function of what I call a smartness of the grid. And although this particular webinar is not really about smart grid, but the fact how you utilize the resource, again, with all the variability and other challenges that we have, is really dependent on how the power grid can accommodate and sort of work in conjunction with that resource in terms of making the most out of that. So the smartness of the grid, and again, how we manage the reactive power, how we manage the reserves, and how they manage dynamics of it, I think it's really really important. And this is where, again, I strongly feel there's an untapped opportunity in the industry. We could move to the next slide, please. Again, that goes with the requirements for the reserves, but this shows sort of a time function, if you will, of how these different variable resources generate power. And it's a busy slide. I mean, we don't want to go into details of what these things really show, but the message there is that the variability is indeed quite significant. But I can sort of turn this around, and the fact that we have all these different curves on that particular snapshot of 24 hours, it's just basically one-day snapshot, it shows that there is a complementary nature of these different blocks of renewables, if you will. And again, if there is an intelligent control and intelligent synchronization of these different resources with the grid, then a lot of the variation can be, if not eliminated, at least reduced to a significant degree. If you could move to the next slide, please. That is another interesting slide that sort of goes beyond just wind energy, where the different sources of the renewable energy can be also intermixed. So you think, for example, a solar energy is clearly varying with the 24-hour cycle in the day and night. Wind energy, depending where it is, of course, but wind energy also has often that 24-hour cycle, and it tends to be in many locations actually stronger at night than during the day. So again, we're talking about this complementary nature of just those two resources. They, depending on where we are, of course, but they can sort of help each other in terms of balancing some of the energy output. And again, if you could go to the next slide, it shows some of the other challenges that the connectivity faces. And let's just go one by one through some of this. The first one is quite important. It's called the write-through. And again, systems or grids experience short circuits or faults. Things happen all the time in different places, in the transmission grid and distribution grid and substations and so forth. So in order to continue or keep the grid operating during the fault and also to recover after the fault, often the system operators require that the resource or the energy source stays online, which is called a write-through. And some of the early technologies had some problems with that because the devices or turbines connected to the grid could not tolerate this kind of voltage collapse. But it's been largely overcome, and it can be managed now at a much better degree. The second one is quite important, and we'll talk about this even more later on, is a reactive power. Again, during faults in system, during major system disturbances, the reactive power is what the system really needs. So when you have a short circuit, and most, if not all, the short circuit are really reactive or inductive. Short circuit actually consume VARs, if you will. Well, these VARs have to come from somewhere. So in a conventional synchronous machines, obviously they come from the hydro plants or nuclear plants or whatever. and in wind plants, we have to do the same thing. We have to be able to support reactive power during these major system disturbances. Then we look at another one, and it's sort of almost an opposite to the bullet number one, when in particular it's maybe for smaller installations and sort of medium voltage networks, where if the voltage is lost, if there's a loss of voltage, that some of these should actually disconnect from the system because it basically prevents feeding the grid during the disturbance, during the short circuit. So it, in some cases, should actually disconnect to prevent the imbalance and also prevent the supplying the grid from the renewable resource. So it's not one sort of fits all kind of requirement. It really depends what grid you connect it to, and if it's a transmission grid and it's supposed to help support the grid during disturbances, or it's supposed to disconnect if the grid cannot continue with this power. And finally, there's many more effects, and again, I just mentioned power quality and harmonics, and in some cases could also be a problem. But all of these actually point out again to what I call controllability. The more of a control you have over the resource and how these resources behave, either under normal conditions or under stress conditions or major disturbances, is really, really important. If we could move to the next slide. So let's just briefly touch on some of what I call solutions in wind energy, again, particularly in terms of connectivity to the grid. Well, the major message, the main message, I think, that I see in this industry is the use of power electronics. It really changed, or it really enabled the wind energy, I think, to be at that commercial scale that we have right now. I mean, wind energy is not new. I mean, we know, I mean, 100 years ago, I mean, people used this for irrigation on farms, and then electricity production of wind again goes back many, many years. But the power electronics is really what changed the landscape, and it really plays a major role. And it's not only from the turbine point of view, which is typically double induction generators, but also from the point of view how these turbines with the power electronics can again be controlled, or can ride through, or can provide reactive power based on, again, system connectivity requirements. This particular example that I'm showing here, and again, we're not going to go into details of the specific circuit topologies and so on, but this particular example shows the full-scale 4-quadrant converter, which again allows for, as the name suggests, for the 4-quadrant controllability of the wind turbine when it's connected through this kind of device to the grid. And one thing I also wanted to mention at this point, that modern power electronic devices or power semiconductor devices that are used in these kind of power electronic solutions really become so efficient now that they really successfully compete with, let's call it, conventional technologies that we know from the past. So it's no longer the problem of losses or incredible heat dissipation and so on. Again, the efficiency from the topology and as well as semiconductor point of view is really something of unprecedented scale. And could move to the next slide, please. And this is now perhaps for maybe larger installations, but the direct current is a message from this slide. HVDC as well as HVDC light is it's our term for using these kind of systems. But basically, it's a voltage source or current source inverter technologies that allows AC systems to be converted to DC for either transmission or interconnectivity. And at the first step, the industry discovered that for offshore installations, HVDC is really advantageous for a number of reasons. The marine cables for making sure that we can collect this wind offshore and then bring it back to onshore in bulk power, and then convert it back to AC and inject it to the grid. There's also advantage of stability, and again with the long connection offshore and so on. So again, both the current source inverters and voltage source inverters play a major role in wind energy, and we'll probably see more and more of these installations as we move forward. The direct current is a unique a proposition, not only for wind energy, of course. This is not unique to wind energy. It just finds itself as a unique application that could utilize, again, the offshore installations, offshore wind farms. You could move on to the next slide. Well, that's another chapter. Let's talk about energy storage, and this particular slide just shows the battery energy storage. But energy storage in general, again, is a very complementary subject to the variability that we're talking about. So, yeah, the wind blows, it doesn't blow. Sometimes there's too much of the energy. We don't have the load that really requires at that very moment, and sometimes it's not enough, and what we're going to do, and so on, and we need the spinning reserve. Well, if we only had an adequate, commercially scalable and attractive energy storage, obviously many of these challenges would virtually disappear. And one of the solutions that is already commercially available is a battery energy storage. Battery by itself, again, is another subject for a long webinar, but it found itself already in commercial installations. Well, you can look at this in sort of a couple of ways, if you will. And you look at the right-hand side of that particular slide. Obviously, the battery has to be charged, and obviously you can discharge when the energy is needed. So that provides a buffer for the variability of the wind. And depending on the specific technology and the battery and the rectifiers, or these cycles, if you will, could vary. But the interesting thing is, and I think we'll talk a little bit more about this in a few minutes with the next presenter, that you could also combine the static VAR compensation with energy storage, and that sort of becomes two-in-one kind of solution, because we did talk about the VAR requirements for the grid. We know there's a variability, you need the storage. You could actually come up with a solution that is a combination of both of those requirements. So that's something that again the other presenter will be talking about, I think, a little bit more detail. The one thing I also want to mention it here, which is perhaps maybe a little bit of the future kind of subject, but in a correlation between the variability of the wind or the renewable resources and electric vehicles. And I know we don't have them yet in a large scale. They're just popping up here and there. But it's very interesting that if you assume large deployment of electric vehicles, that actually, you think of this, becomes a distributed energy storage. And if, again, somehow, I go back to that smartness of the grid or intelligence of the grid I was talking about, if, again, the grid could be made intelligent enough to utilize this distributed high-volume energy resource from the electric vehicles, and somehow combine or marry this or synchronize or control this together with the variability of renewables, I think we will have a win-win-win situation. If we just move on to the next slide, please. This one is about safety, and we at ABB clearly put safety as one of the most important aspects of any power or systems that we're dealing with. And safety obviously has to do primarily with people, protect personnel, people who are near the equipment they operate or utilize or somehow happen to be around the equipment. But also protect the equipment itself, or protect the system's integrity or security of what the system should do. So it is a high priority. And what I'm listening here, again, without going to much of the technology details, are some of the aspects that we really address in terms of safety. And arc flash is probably one of the most known or the most talked about effect, where the arc ignites, just as for information, the arc ignites directly in proximity of a person or personnel being around it, and the energy of the arc, particularly thermal energy, is something definitely harmful to people around it, and that it can be dealt with in a number of different solutions, and obviously technology solutions are probably the most preferred ones, because they can prevent or dramatically reduce some of the effects of the arc flash. And here the arc flash detection, particularly the detection by light or by fiber optic sensors, is something very important, that if we could detect the arc flash in a very early stage, we can definitely minimize the effect of it. The next one that shows arc resistance equipment, and again, there is a category of equipment in ANSI or IEEE standards that is defined as arc resistant, and that has to do with the construction of particular equipment, being a vessel, being an enclosure or cubicle or any other equipment of this kind that can contain the arc if there is a fault, if there is a short circuit, obviously unintended short circuit, that this equipment can contain the arc again and not harm the personnel, or even not damage the adjacent equipment. So there are different categories of this, and again, I don't have time to go through all this, but the arc resistant equipment is something that people should know about, that it's available, particularly in the context of wind energy industry, which I consider is still a relatively new industry, although been around for many years, but compared with the utility industry or other power system applications, it's still relatively new, and often people don't know that there is a category of equipment that could actually contain the arc successfully. Another one is arc killers, and UFES is just an acronym for what I call the ultra-fast earthing switch. And again, it's another kind of device that can very quickly, in the order of millisecond or so, basically short or shunt the arc to ground, and therefore basically extinguish it, and again dramatically reduce the effects of the short circuit. And next one is fault current limiters, again FCL category, where again these are very fast devices that basically insert the impedance into a circuit and therefore reduce the fault current, or completely interrupt the fault current, again in a very, very short period of time. So these are not circuit breakers as we know them. They are not the conventional devices like we use for switching power. These are devices that operate in a quarter of a cycle of a 60 hertz or less. So I mean, talking about a less than 4 millisecond operating time, and therefore, if you act so quickly, you basically limit the very first peak of the short circuit current that you have. And finally, the personal protective devices, PPE, is something that we all should be familiar with in this industry. And there are a number of guidelines and standards in the industry, like the NFPA 70E and so on, deal with the PPE in terms of electrical safety. So these are just some of the very quick reviews of what we have in terms of challenges and potential technology solutions. And I would like to pass it on to Joe now, and he can talk about applications.
Okay, well, thank you, Mietek, and good afternoon again to everyone. So what we'd like to do now is actually walk through a couple specific examples for where we've applied power conversion solutions specifically for wind integration. And before we jump into these examples, just a couple of background slides and into the discussion of these solutions. So I think historically, when we talk about grid interconnection solutions and specifically for power conversion, I think the discussion has always gravitated naturally more towards meeting grid code requirements, meeting interconnection requirements from a utility perspective. What we've seen, I think, over the last few years, and I think Mietek alluded to it in his previous slides, with the advancement and the emergence of some of these power conversion solutions, and specifically on the energy storage side of things, the discussion has expanded not so much to focus just entirely on the grid code compliance side of things, but also onto, let's say, the performance enhancement that these solutions can afford the renewable plant. So when we look at an example of, let's say, a very common wind project, you can kind of look at these solutions from two perspectives, one from the utility and grid side of things, and then the other from the renewable plant. So, from the utility and from the grid, generally speaking, really ideally, the whole intent, for these solution options is for that wind farm to really operate very stably, not adversely affect anything from the grid. On top of that, in an ideal world, the utility would like this renewable plant to actually provide regulation facilities comparable to that of a conventional generator. And these tend to be things such as reactive power, voltage control, and frequency response, some of the things that Mietek alluded to in his slides. If you look from the perspective of the renewable plant, the first step is always to understand those grid code requirements, understand the technical hurdles needed to connect to the grid. But what we're finding is that there are a number of, let's say, value adds and performance enhancements that these types of systems can actually give to the renewable plant. And specifically on the energy storage side of things, we're seeing a number of, let's say, neat applications where there really is the potential to enhance really the value and the revenue stream for that plant. So when you look at things from the renewable plant, you kind of start looking at things such as enhancing the reliability, making that plant more durable, actually putting higher quality power out into the grid, and perhaps things such as smoothing and capacity firming, things that can keep that meter spinning and put it extra value into that renewable plant. These are a number of interesting things we're seeing with some of these projects that we're involved in. If we can go to the next slide, please. So when we talk about power conversion solutions, it does really, let's say, begin and end with meeting those grid code requirements and interconnection requirements. And those of us and probably quite a few of you that are listening in that work in the wind industry and have familiarity with the various grid codes, it really is fair to say that these grid code requirements, these interconnection and technical requirements do tend to vary quite significantly region to region, utility to utility, and even the location on the grid. And there's a number of technical reasons for that, and it really does make sense from let's say a planning perspective. The wind farm is going to have the greatest effect locally on the grid, and then out more onto the network depending on how large the facility is. So that being the case, even though these interconnection requirements do tend to vary region to region, what we do tend to see is that they all kind of have, let's say, the similar or more or less the same subcategories. And again, these then do tend to have more to do with the stable operation of the grid, low voltage ride-through, high voltage ride-through, things that are important for the stable operation of the grid from the utility perspective. In addition to that, I did mention this on the previous slide, ideally these wind facilities also will provide facilities that are comparable to conventional generators in regards to reactive power, and voltage regulation, as well as frequency response and ramp rate limitations. So what we're seeing with these power conversion solutions, and again, these are related more to energy storage solutions as well as reactive power compensation, is that really with the advancement of these power electronics, as well as storage technologies such as batteries, we've got a very highly customizable, dynamic, and adaptable type of solution that we can now apply to wind facilities. And what we're seeing is it's no longer just enough to meet these grid codes, but we really do look to enhance the overall performance of the wind facility and provide a lot of these traits again that we see in conventional generators. So the ability to provide both active and reactive power, as Mietek alluded to, on a dynamic basis, and then have the controllability to customize these solutions not only for the wind farm, but also for the location on the grid, depending on the faults that you're trying to support and things like that, and ramp rate requirements. We're seeing that these systems are very, very adaptable and customizable and programmable, and are therefore very good solutions for these different challenges. So if we go to the next slide, our first example is of an energy storage system being implemented at a wind facility in Saskatchewan, Canada. So a little bit of background on this project. The Saskatchewan Research Council did team up with a number of entities to essentially demonstrate the different value adds that energy storage can give to a wind facility. There was a whole list of things that they wanted to, in essence, test and qualify in terms of the different performance out of this type of system. But really, the main focus was to really understand the control algorithms and really get a good feel for the smoothing effect and the capacity firming capability of a storage device when coupled to a wind farm. On top of that, of interest in this region was the ability to reliably dispatch the energy storage device, specifically during peak times, to potentially participate in demand response programs. So, from a technical perspective, and Mietek had a good slide on the variability challenges that come along with wind facilities and the stress that they put on the grid because of that, just to handle that. And really, the intent here was to demonstrate not only, let's say, potential financial benefits that come from a more constant form of energy, but also the technical challenges that are alleviated by implementing the storage device. So you can see from this picture, it's a very small facility. It's actually a single turbine facility with a lithium-ion battery, and then the power conversion system with the site controller. And again, really the intent here was to understand the control algorithms and understand the performance that they could potentially get out of this type of system. So if we go to the next slide, this system has actually been in operation for the better part of the year, and we've actually got some very good field results from it. In this slide, we're actually looking at the results of the smoothing algorithm and the performance that we've seen on this single turbine. So, the one thing I will mention, and I think Mietek mentioned this in his slides as well, certainly, volatility is definitely a function of size. So in other words, the larger the wind farms, the more turbines you have, typically speaking, the variability and the volatility decreases with that. So, this demonstration project being a single turbine installation, certainly the volatility that you'd see, let's say, compared to a normal wind farm or a larger wind farm, certainly is amplified. But, again, this being more of a demonstration type of project, we were able to definitely qualify the performance of this control algorithm. So real quick, I'll describe this graph here. We're plotting three things, and if you look at the upper portion of this graph, in the light green trace, we're plotting the megawatt output of this single turbine, and you can see pretty clearly, as expected, highly variable, pretty jagged, many peaks and valleys. On the bottom part, in the red trace, we're actually plotting the active power output, the charging and discharging of the battery energy storage system. The aggregate or combined result is in that blue trace, and you can see very clearly the smoothing effect, or really taking the edge off of the variability that battery energy storage system has on this facility. The other nice thing that we're able to capture on this graph is sort of a with and without, or before and after effect. So there's a period of time towards the end of this plot where the energy storage system is essentially turned off. It's not charging or discharging. So you can see very clearly that when you take that energy storage device away, the volatility increases pretty significantly. Obviously, it's just a single turbine that you're seeing. You can see it's very dramatic. Ramp rates are pretty significant, and you get a highly volatile output from that plant. So a couple of the, let's say, specs that came out of this, volatility in this case was reduced by 64 to 65%. So again, this being a single turbine installation, that figure is a little bit amplified, but we were able to show very clearly the ability to decrease that volatility. In terms of, let's say, a grid code compliance standpoint, we were able to show that ramp rates were able to be decreased by a factor of 20. And so applying that to, let's say, maybe potentially an island grid such as Puerto Rico, which is the focus of our next example, this type of system is not only beneficial for the performance of the plant, but is actually required per the grid code. So the evaluation is ongoing. Really the next step with this plant is to understand to what extent the capacity factors and availability can be improved, and essentially potentially add some dollar figures to that, and understand how much more valuable can that plant be in terms of the owner-operator. So if we go to the next slide, one of the things that they were very interested in is understanding to what extent the battery can be reliably dispatched. So, nothing too significant here in terms of, let's say, a technical requirement. Really what they want to just understand is, especially during peak conditions, could they rely on that battery energy storage system? Could it be dispatched, and could they essentially participate potentially in a demand response program? And, very clearly what they saw is, on command, very quickly, they were able to get the response that they required and that they expected out of that energy storage system. So, when you look at the kind of the key takeaways, and again, the system and the evaluation is ongoing, they were able to demonstrate very clearly the effect of the smoothing and the capacity firming algorithm, and its ability to really make that wind facility look more like a constant form of generation. It's not as highly variable. In addition to that, sort of as a value-add feature, that energy storage device could be dispatched at peak times to potentially participate in that demand response program. So two key aspects really not seen traditionally in wind installations, and really major value adds in terms of what this facility would see in performance. So if we go to the next slide, our next example is really what I would call a very much a classic dynamic VAR compensation for grid code compliance example. So a little bit of background on this project. It's actually a roughly a 23 megawatt wind plant in Puerto Rico. So anyone listening in on this call that's involved in either wind or solar, in all likelihood you've heard of PREPA and probably have heard of their grid code requirements. I'd say just based on my experience, it's definitely one of the more stringent grid codes that really I've encountered. And when you talk about, we did speak before about different grid codes and why they do vary region to region and utility to utility. Puerto Rico obviously being an island grid, it's not interconnected. It doesn't have, let's say, the same robustness as we have here in the States with our interconnected grid. There are major stability concerns, in terms of variability in wind and PV assets and their adverse effects on the grid. So in reaction to that, the utility, PREPA, has implemented these technical requirements, and really, from their perspective, it's a necessity to ensure a stable operation of the grid. So, dynamic compensation, certainly, dynamic VAR compensation is nothing new. It's actually been implemented pretty widespread, I would say, certainly in the more mature markets. So in this instance, really, there were two primary objectives for this VAR compensation system, and really the first was to comply with the local grid code requirements as it pertained to reactive power as well as voltage control. But just as importantly, kind of a two-way device, so to speak, it did offer a level of protection from both low voltage as well as high voltage events that emanated from the grid, and protecting the turbines from potentially tripping offline and really adversely impacting the operation of that wind farm. So if we go to the next slide, As is very common with these installations, there typically are multiple reactive power assets. So as is the case with this example, the wind turbines themselves actually had power converters very similar to that slide that Mietek had just shown that could provide a source of dynamic VARs on their own. In addition to that, very common with these plants, there's also a steady state reactive power requirement that require the need for mechanically switched devices such as capacitor banks as well as a reactor bank. And this is all in addition to, in this case, a 12 megavar STATCOM. Really from the utility perspective, they do not disseminate, let's say, between wind turbine VARs or reactive power or wind turbine, STATCOM VARs or static devices. From the utility perspective, from the point of common coupling, it is all one system. It is all one voltage regulation device. So as Mietek alluded to, the ability to control these devices as one system and to do it elegantly and stably, does present certain challenges. In this case, there was a coordinated effort between the power conversion system, the STATCOM controller, as well as a wind power plant controller. There had to be kind of a natural exchange of controls as well as exchange of data. Again, from the utility side, they really don't disseminate where those VARs are coming from. They just need those VARs, and it has to comply with the grid code. On top of that, which is very common for these type of applications, there's typically a number of things going on at the same time. So even though the grid code really only cares about what's happening out in the transmission grid, participate in voltage control and give me the reactive power we need, the system is also offering a level of protection for the wind turbines itself, and that, in this case, is really handled by the short-term overload of that STATCOM. So two things going on at once: regulation of the transmission system, as well as what I'd call fault protection, both low voltage fault protection as well as over voltage protection on that 34.5 kV grid. And really those things are happening at the same time, and is really required to ensure that wind farm does not trip under stressful fault conditions and make a bad situation worse. So if we flip to the next slide here, so this system has been operating, I think, a little bit over a year now. We've gotten some very good field results as well. So that plot I'm actually showing there on the left, again, anyone that has familiarity with PREPA or has worked in Puerto Rico understands, very demanding modeling requirements and simulation work. So, what we're showing there on the left is the control approach and the ability for these multiple reactive power assets to operate together and operate as one integrated system. On top of that, we've already harvested a number of good, high-speed events of both low voltage and actually more frequently over voltage conditions at this wind farm location, and we've seen instances where over voltages have gotten as high as 1.3 per unit, which is about as high as I've ever seen, at least in my experience. So we've been able to see the system operate very well and basically be able to be controllable per the grid code, as well as offer a high level of protection for the wind turbines themselves. So if we go to the next slide, really in conclusion and some of the key takeaways, as Mietek pointed out, there are no shortages of challenges, in terms of interconnecting wind to the grid. It's very much dependent on what type of turbines are being used, location on the grid, how strong that grid is, and things of that nature. So really what we promote is, very early engineering, early planning, early consideration for all of these various challenges as they pertain not only to the wind farm but to stable operation on the grid. It's very critical to understand these challenges and plan for them ahead of time. For that second bullet point, Mietek mentioned this a number of times, having smarter controls, a smarter controllable grid. We're seeing with the emergence of these power conversion systems and specifically with energy storage devices, VAR compensation, things like that, we really do have a higher degree of controllability and much more elegant technical solutions that we can apply for these wind systems that can be very good solutions for it. And that last bullet point, hopefully what we've demonstrated via our two applications is that energy storage as well as STATCOMs and reactive compensation really are very good solutions in terms of that controllability and smarter solution options, especially compared to, let's say, conventional solutions for really adapting to the grid and being customizable to the wind farm. Not only meeting those grid code requirements, but also adding value to the renewable plant itself, potentially both financially as well as from a reliability and availability standpoint. So with that, I think I'll turn it back to Sarah for potential questions.
Thanks, Joe, and thank you, Mietek. That was a very informative presentation. Thank you to the audience for attending today's webinar. If you enjoyed today's webinar, I really encourage you to sign up for other webinars in our WIN series. You can find more information about them at www.abb.com/us. We will now open the webinar for questions and answers. A reminder, if you would like to ask a question, please use the question box on the GoToWebinar panel. We will answer as many questions as possible at the end of this event, and Dennis McKinley will take care of asking the questions to our speakers. Dennis?
Thanks, Sarah. And special thanks to Mietek and Joe. You guys did a great job. And thanks to the folks that have already sent in a bunch of questions and also some compliments, so thank you for that as well. Some of the first questions that came out, what type of energy storage systems, battery, flywheel, ultracaps, are we seeing in wind applications? I guess that goes to Joe.
Yeah, that's a good question, and really, it does depend on a number of things, really. And first and foremost, what is the application? Here at ABB, we don't actually manufacture, provide the storage mechanism. We focus on the power conversion systems and control. So depending on whether it's a power application or an energy application, and people that are more familiar with battery chemistries and technology can speak way better than I can, but depending on that application, you would potentially look at, let's say, a power battery or an ultracap versus maybe an energy battery. But really the short version of the answer is that we see all three technologies implemented. I would say battery technology has definitely been more prevalent, specifically lithium-ion technology more for some of the power applications as it relates to smoothing and ramp rate response for some of these applications. But no reason that all three technologies couldn't be used in these cases, and we have already seen applications where all different technologies are utilized.
And
thank you.
If I could add to it, and it was a great question. The batteries seem to be the most commercially available, especially at the large ratings, as compared to some other technologies. We don't see much of a flywheel yet. Again, flywheel technologies tend to be a rather short-term smoothing effect. These go for tens of seconds rather than hours. And interesting, I could just add to the mix and perhaps challenge all of us, audience as well, in terms of how the fuel cells might find its way to the wind energy industry as well. And clearly there's also an old-fashioned pump storage or hydro pump storage facilities where you can definitely utilize the stored energy in terms of the water pumping up and down. But the battery is probably the most commercially available and deployable. And I think, just to mention one sort of a record installation, as far as I remember, the largest battery in the world in the power system installed today is a 40-megawatt facility in Alaska, where, again, this battery bank can provide I think 40 megawatt hours, so 40 megawatts of power for about 1 hour, or 4 megawatts for 10 hours. So it depends how you utilize the battery.
Mm-hmm.
So these are again commercially sizable to about small, medium wind farm projects, and we'll probably see more of this coming up.
Good. Guys, the questions are coming in quick, so I'll try to run through these. This looks like it's a question for Joe. What is the length of ride-through time required for voltage stabilization?
Yeah, that's another good question, and it does very much change. Grid code. The most stringent I've seen is actually the Puerto Rican the PREPA requirement. It's actually a zero voltage ride-through requirement for up to 600 milliseconds. which is quite a bit longer than typically what I've seen. Traditionally it's been maybe on the order of 100 to 200 milliseconds. A lot of times it's dependent on protective equipment, how quickly a fault can be cleared, and that tends to be utility and regionally, a function of what things are done regionally. But yeah, that's very much something that varies region to region.
Thank you. This next one, I'm not sure if we can handle on the webinar, but we'll try to get an answer back to you. What happens with the HVDC platforms for offshore wind farms in case of a tsunami? What I would say to that up front is I know the turbine OEMs work very hard on proving out the capabilities of their turbines to withstand very high winds and tsunami, obviously. I would assume the same thing with the HVDC platforms, but we'll have to get back to you with an answer from our experts on that. Next question, looks like it's to Mietek. Do you think that in order to succeed, the wind industry needs a large-scale energy storage close to wind farms or small-scale community-based storage closer to the load?
Well, great question. I think the quick answer is both. Clearly, if you had large energy storage right where the wind farms are, that will be a very nice complementary effect between those two. However, not always it is practical, and also, as I think I mentioned in one of the slides, this sort of a futuristic, perhaps, effect of the electric vehicles if they really come online in a large volume. So it would be more of a challenge from the grid point of view, and again, connectivity, if you have the energy storage remote to the wind farm itself. But I think both solutions are possible. The ideal solution would be to be close to large wind farms. However, if it's not possible or not feasible, or if other energy storage resources are available distributed through the system, you still should be able to do it, but it will require more intelligence of the grid.
Okay. This looks like for Joe. Do wind farms that utilize wind turbines that have reactive power output capabilities still need supplemental reactive compensation systems?
Yeah, and really what we've seen is the answer to that is yes. We do see instances where even though some of the more modern turbines and larger turbines, the Type 3 and Type 4s that do have reactive capability, depending on the grid code, there are many instances where they do require supplemental reactive compensation systems, and these tend to be grid codes that still require VARs even at 0 megawatt output and things of that nature. So it's not entirely widespread. There are many instances where turbines can meet these grid code requirements on their own. But even though some of them that would appear to be able to meet them on paper, we do see instances where they still would require potentially a STATCOM or a storage device.
Okay. Question looks like for Joe. Please share more detail on the effects on ramp rates.
Yeah, so that's an interesting question because in theory, ramp rate, if you think about the severity of a ramp rate, if a wind farm, let's say, drops out very quickly, and maybe the most extreme case, and this isn't really possible, it goes from full output to zero. As Mietek alluded to in his slides, some sort of reserve needs to come online to compensate for that, or to fill in that gap. So depending on the grid, depending on the assets that are available to you at that time, there could be a period of time where potentially a renewable facility drops out, and you really can't get those reserves online for whatever reason that might be, and you could potentially be into an instability or stability issue rather. In addition to that, ramp rates can affect, depending on the robustness of the grid, can have an impact on frequency, and that, of course, can impact a number of things. So, island grids such as Puerto Rico, very concerned about the adverse effects of ramp rate, and that's why the way they've written their grid code, they've more or less dictated that energy storage devices are needed, especially for both PV and wind. But yeah, there's no shortage of things that I guess can arise from severe ramp rates, and certainly we see that especially on island grids.
Thank you. And I apologize to the audience in advance. We've got a lot of questions that came in, and we're not going to get to them all. I got time for probably one more. We will get responses back to you, within the next couple of days after the seminar's finished or webinar's finished up. But this one looks like for a Mietek. All of your technology solutions involve power electronics, but power electronics incur losses. Are we adding to the problem of overall grid efficiency?
Well, yes, it's a good question. I mentioned to you the power electronics devices and the system solutions are much more efficient than they used to be 5, 10, or 15 years ago. So we are talking about the efficiency of mid to even high 90%. Are they adding to the problem? I don't think so. However, there is a price to pay. Clearly, you have, there's nothing for free here. There is obviously some losses in this single digit, but I think the price to pay is so small compared with the resource and the benefits that the renewable can provide to you. So I don't think that power electronics, from the losses point of view, it really adds to the overall problem that much. In fact, if you look at the entire power system and just diverge from the wind energy, it is power electronics that enable the modern society, all the way from generation, in this case wind energy, down to the load. I mean, if you look at the entire power system in the value chain, there's more and more power electronics everywhere, both from the load side and from the source side. And it doesn't seem to be really affecting the system that much. In fact, the efficiency go up. So I don't think that really is a major problem.
Okay.
Thanks, Mietek. I think our time is up. So, Sarah, if you wouldn't mind wrapping it up.
All right. So thank you to all of our speakers, and thank you, Dennis, for moderating those questions, and a big thank you to our audience. Just wanted to let you guys know, when you close this screen, you will see a short survey of today's event. We really appreciate your feedback and comments. Thank you very much, and have a great day.